Hello, this is Group 3's presentation of Chapter 15 of Peirce's Types in Programming Languages. My name is Adam Johnson. Along with me presenting will be Mac May and Andrew O'Brien. So, Chapter 15 of Peirce's textbook is titled Subtyping. And before going into discussion of specific sections of that chapter, I'm going to do a quick recap of some previous chapters, specifically Chapter 8, which introduces typing in the simply typed lambda calculus. So in previous chapters, Peirce set up the syntax for arithmetic expressions being constant true, constant false, conditional, constant zero, successor, predecessor, and then the test for zero is zero. Conditionals, of course, were set up via if, then, else. And then evaluating a term could result in values of either true, false, or an additional numeric value. And then for numeric values specifically, there is the zero value and the successor value. So Booleans and numeric values were sort of what this original type system in the lambda calculus was introduced as. And you can see how this might be very restrictive. And what will happen is a type checker sort of interpreting terms of this nature will very often get stuck. For example, if a term like if true then zero else false is introduced, because there is no type polymorphism, that can easily can lead to a stuck state. So what's needed is typing rules for variables, for abstractions, and for applications. And we can see through the so-called arrow system of the simply typed lambda calculus how we can create more sort of robust and polymorphic types that don't lead to these stuck states. So subtyping is also known, as I've mentioned this term multiple times, subtype polymorphism. Simply the idea that types are not just restricted to being Booleans or numeric values. This has implications on most other language features. And programmers will find this most familiar to the concept of object-oriented programming. So the idea that within a language like Java, there are objects that can be polymorphic. They're not simply limited to being of a certain type is the idea behind subtyping. So you can see on our third slide, the first section of Peirce's chapter deals with subsumption, and this just introduces the notation in the simply typed lambda calculus for subtyping. So he motivates this with a typing rule that maps to results of T12 T1 over T12. And then he provides a term that only maps to a single output. So because the rule is looking for two outputs, both x and y, when it's given a term that produces only x, this leads to the aforementioned stuck state. But we can see that that only one input is required because when the T1 was provided, we got the result of T12, which is what's in the denominator of that rule. So subtyping allows us to overcome that challenge by saying that one term is a subset of another. So in slide 4 here, we see the notation wherein S is a subtype of T, inversely, T is a supertype of S, and that means that S can be used safely whenever T is required. This doesn't say anything about the restrictiveness of T, but what it says is that S can exist as a replacement for the type of T. So you can see that on slide 5 here, the rule of subsumption, since S is a subset of T, then by extension, every T in S is also an element in T. So that would resolve the previous issue wherein two values were being looked for, but only one was provided. Because X is a subset, then that can be used as a subtype to provide the output that's looked for. Just a couple of sort of features of subtyping introduced slide 6 here. So subtyping is transitive. So if S is a subset of U and U is a subset of T, then S is a subset of T. So when it comes to understanding the number of required fields, we refer to the with subtyping rule. So what this means, perhaps surprisingly, is that the more types that are provided in a record, the more restrictive it is. Going on to slide 7 here, we can see that, for example, if there's a record type that's simply a X natural number, then what's required is a natural number X, but then that can be in combination with anything else, whether it's a Boolean or additional natural numbers or any other types. That's the only requirement. But if we have a record type that requires X natural number and a Y natural number, there's that further requirement from what we previously looked at of a Y natural number. So now you need X natural number, Y natural number, plus everything else. So that might be a little counterintuitive. And that's expressed also via the depth subtyping rule. Moving on to slide 8 here, we can see that width and depth subtyping can be used together. It can also be done for a single field, and via the transitivity rule that was introduced, fields can be dropped. You can see how that progresses with the B natural number below, wherein through transitivity, you can chain subtypes to drop those that are unnecessary. Chapter 9 just talks, sorry, not chapter 9, slide 9 rather, just talks a little bit more about the nature of subtyping relations. So you can permute record types. So for example, if you've got a specific permutation of C top, and I'll talk shortly about what top means. So you've got C top, B bool, A natural number. You can simply permute that to A natural number, B bool, C top, and they are equivalent. Moving on to slide 10, you can see that functions can also be created as types and subtypes, but there is a lot of sort of careful tracking that needs to go between the subtyping and the outputs. So we can see here that S2 is a subtype of T2, and we can also see that T1 is a subtype of S1. So T1 being a subtype of S1, we can see in the denominator that S1 creates an output of S2. So T1, therefore, being a subtype of S1, a type that is essentially a replacement for S1, it can also replace S2. S2 being a subset of T2, that does not inherit any outputs because, as we can see, T2 doesn't map to anything. Additionally, with S1 being the supertype of T1, that doesn't necessarily mean that S1 maps to T2 because of the subtype relationship. We can see in slide 11, through the use of the abbreviated types there, the author's just saving space, that the X natural number alone can be used for the typing rule for function application. That concludes the first two sections of PLP chapter 15.
Properties of typing and subtyping. We must make sure that preservation and progression hold true in the presence of subtyping in order to keep our terms safe. We must make sure that subtypes of functions have the same general parameters of the types from which they are derived. This means making sure that the elements to the left of the arrow remain contravariant and the elements to the right remain covariant. Similarly, subtypes of records need to deal with having more fields than the original, maintaining certain standards of order, and keeping certain relationships intact. In other words, if S is a subtype of the function T1 to T2, then S has the form S1 to S2, and we know that T1 is a subtype of S1, and S2 is a subtype of T2. Each of these can be proven via straightforward induction on typing derivations. Next, we need to make sure that the typing relation has a substitution lemma. The same one from the prior section can be applied once again. We prove it by induction on typing derivations. New cases for the typing rules tRecord and tProject are required, but they can be gathered with straightforward use of the induction hypothesis. The preservation theorem is complicated at several points by the addition of subtyping, but in general, the statement remains exactly the same as earlier. Essentially, in a given context, if t is of a certain type, and t runs through a function produces a second term, that second term will be of the same type as the first. We prove this with a straightforward induction on typing derivations. We've already learned the proof of preservation for simply typed lambda calculus, and these will all be similar. A few additional cases are needed. In the case of t-variance, t equal x cannot happen as there is no evaluation rules for variables. In the case of t-abstract, that also can't happen since t is already a variable. The case of t-app can be derived in 3 different ways, via e-app1, e-app2, and e-app-abstract, so we check each one. The case of t-projection also has subcases, e-projection and e-projection record. The case of t-sub is simply that if a given term is of type S, S is a subtype of type T. And these are all the cases we must add to account for subtyping and prove preservation. We next prove that well-typed terms cannot get stuck even with the addition of subtyping. The canonical forms lemma explains the possible shapes of values belonging to the 2 types we're discussing here, functions and records. At this point, the progress theorem is very near to what we've already proven for simply typed lambda calculus. Canonical forms lemma has taken care of the vast majority of issues which arose from subtyping, so we only need a few more changes, none of them drastic. We needn't worry about the variable case as t is closed. Abstractions are values, so lambda abstractions are handled trivially. This leaves us with only a few additional cases. The case of t-app, since t1 is either a value or capable of making a step of evaluation, we can either apply e-app1, e-app2, or e-app-abstract to t. Either all ti are values, in which case t is a value, or one of them can make a step, and we apply rule e-record. And finally, the case of t-sub is that in a given context, if t is of type S, then S is a subtype of t. The induction hypothesis applies here directly.
Continuing on to section 15.4, Peirce discusses the top and bottom types of subtyping. So first he introduces the type top, which is more commonly used in practice. And this is said to be a supertype of every other type, types being, as we've discussed, things like Boolean, natural numbers. And this is a maximal type in the simply typed lambda calculus. So once again, drawing a parallel to object-oriented programming languages, top could really be said to be equivalent to the concept of object in and of itself. So what this does then, it's a technical device that combines subtyping and parametric polymorphism. So these are basically data types that are generic. They're needed, for example, when functions are performed on multiple undefined types, when you sort of want to leave things wide open and undefined, when you can't really say what the types will be restricted to. So top is the supertype, and it doesn't lend any further restrictiveness whatsoever. Conversely, bottom, or bot, is the inverse of that. It's a subtype of every other type. So essentially, it's the minimal type used in the simply typed lambda calculus. So it doesn't contain any values for types, and as you can see, this is maximally restrictive, much more restrictive even than the simply typed lambda calculus that was introduced earlier on in the textbook. So this is really useful when an expression is not expected to return any result, since it in and of itself is equivalent to no type, therefore no result. So error in the example that we see on the slide, for the second slide for the top and bottom types, you can see in the expression here there's an if then else statement. So the else is error, and you can actually replace that with the bot type, and that can essentially be promoted to basically be any type from there. So just kind of going through the pros and cons and functions of these two. As I said before, adding top is much more straightforward because it does not add any further restrictions due to the fact that it's a maximal type. Bottom, of course, being a minimal type, adds much further restrictiveness. So, for example, if you had an inference like if an application T1, T2 is well typed, then T1 must have an arrow type. That would change too with the use of bottom to be if T1, T2 is well typed, then T1 must have an arrow type or type bot. So you'd have to sort of, if you were using the bottom type, you'd have to go through and update with that sort of stipulation or type bot because it being a minimal type, at the very least, it always has to be there. Whereas with top, because it's a maximal type, its inclusion is much less tricky.
Subtyping and other features. Everything we add from our initial simple calculus on the way to a fully operational programming language must be tested with subtyping to ensure it all still functions. We'll address now some of the features which have been brought up so far, though these will not include parametric polymorphism, recursive types, or type operators. Ascription and casting. T as T is the ascription operator, a form of check documentation, which allows the programmer to ascribe a certain type to a subterm of a complex expression, and to record this assertion in the text of the program. It can also be used to force the type checker to use an abbreviation which will be more readable to the human than a technical formal type. Ascription will sometimes be known as casting in languages which incorporate subtyping, such as C++ or Java, which is a little more complicated. The typical notation is T, T. Casting can be broadly broken down into two categories, upcasting and downcasting. Upcasting is comparatively simple, while downcasting needs a lot more explanation and involves dynamic type testing. Upcasting simply assigns a supertype of whatever type the program would have assigned to a given term. The term is T, and the supertype is T. If T is in fact a supertype of the term T, the program allows it. This is confirmed using tsub and tascribe. Upcasts are sometimes used to limit access to certain elements of a term in a process known as abstraction. Essentially, if you don't want the user to be able to simply reassign the value of a given variable, you can upcast the object so that the command won't be accepted and the methods cannot be accessed. Downcasts are used to assign a type to a term which cannot otherwise be verified. As you can see in the T-downcast rule, as long as we prove that T1 is well typed to type S, we can assign it to type T, with no limits on what connection T and S must have. It is a dangerous tool to use, since it is basically the human telling the program that a given term will always act enough like that type not to cause errors, whether this can be independently proven or not. If the programmer is wrong, or if things change after the fact, this could become a big issue. Typically, the type checker will accept the type given at compile time, but add a note to check during runtime for this particular potential error. Thus, edowncast verifies the actual type while the program is run with the declared type. If it does not, the term will get stuck. We lose progress and by extension safety if the option to downcast is introduced. Languages generally have two possible ways to handle this: either make the error a dynamic exception that the program itself can catch and handle, or to replace the operator with a dynamic type test. Java uses downcast frequently. Lists, for example, do not have versions for every conceivable type. The single, monolithic list simply holds things of type object, which is the ultimate superclass and encompasses all other terms. When a new object is added, its type is simply upcast to object. However, this runs into an issue when we want to return an object from a list, since type object might not suffice for its intended purpose. Thus, it will be downcast as some type T. And this happens literally every time an object is removed from a list in Java. Many argue that this is a terrible idea, which should have been overhauled and replaced with true polymorphism in the lists, eliminating the name for runtime tests. This is something of an idealistic viewpoint, however, which ignores the many benefits of a system that has proven to function well enough. Variants. Subtyping variants is similar to subtyping records, save that new variants are added rather than dropped when moving to a supertype. This is because adding more labels decreases the information we glean about its elements. A single label means everything has that label, while two labels means any given element can have one of two labels. More variants requires case statements to grow unnecessarily complex and inefficient. Lists. The list constructor is covariant, like most apart from the left side of subtype functions. If all elements are of a list of type S1, and S1 is the subtype of T1, we know that the elements of that list can operate safely as though they were type T1. References. To preserve type safety, References are one of the few cases which must be invariant, neither covariant nor contravariant. What does that mean? Two types must be subtypes of each other in order for either to be a reference subtype of the other, which is fairly restrictive. The order of the fields within a given term may be adjusted, but all else must be exactly the same. This niche case is so that records can be read and written back and forth. If anything else had been changed, at least one of those actions will fail. Arrays. Arrays will also prove to be invariant to allow for both dereferencing and assignment in a manner that will look very similar to references. Java is an exception which allows for simple covariance. While there was initially purpose to this, it's largely now an artifact of a forgotten time, creating more issues than it solves. References again. The addition of source and sync allow for further analysis of references. Source reads but does not write, while sync writes but does not read. As an astute observer will note, reference is a combination of their two abilities. Source here is seen to be covariant, since it's possible to read from a type to its supertype. Sync is contravariant, since supertypes can always be written onto subtypes. This, therefore, makes it clear that reference itself is a subtype of both source and sync. Channel types are present in concurrent programming languages. As far as typing, and thus we, are concerned, communication channels behave exactly like reference cells. They both read and write, and thus must be intravariant. Much like source and sync, specialized channels such as output and input can be contravariant and covariant respectively, allowing for the write and read functions separately without the restriction of covariance. Base types. Subtypes can even be introduced as relationships between primitive types. Many languages have Boolean as a subtype of natural numbers and simply designate true as 1 and false as 0. This allows for interesting efficient expressions, like 5 times b, instead of if b, then 5, else 0. As you can see, if b as true is 1, 5 times 1 will be 5, and if b as false is 0, 5 times 0 will be 0.
Throughout our discussion so far of subtyping, there has been this sort of implicit assumption that subtyping is semantically insignificant. It's formally that it doesn't really change the meaning of our programs, and all it does is give us this added flexibility. And so we might as well then use it. All we get is additional functionality. But using subtyping actually has certain performance penalties. And to get around these penalties, we need to use something called coercion semantics. Some of the problems with subset semantics and subtype semantics are as follows. If you have floating point and integer numbers, they need a common tag representation. Anytime you do a primitive operation then on integers or floats, you need to check what the tag is, right? This costs time. It's a major source of time loss for high performance computing and things like that. It could be too much. There's also this idea of records that would combine with subtyping cause slowdowns. The big idea is that you have to perform searches at runtime if you use subtyping with records, and this is also a major source of slowdown. You can eliminate some or all of the subtyping slowdowns with coercion semantics. What happens is the subtyping is then replaced with runtime coercions. For example, as we mentioned before, you have the problem that integer and numbers need to be tagged. Now, an example is if integer type is promoted to floating point type, you can, instead of having a system where tags are checked, you can just have the compiler physically change a number's representation from integer to float at runtime. The general theory behind coercion semantics is that you can have functions which essentially map subtype languages to lower level subtype free languages. Although this is a sort of general feature, the example most pertinent to this class and to us is this idea of simply typed lambda calculus being mapped to purely simply typed lambda calculus. Again, one simply typed has subtypes and purely simple does not. And Below you can see how each of the three types in simply type lambda calculus has a translation function here. Important in the idea of coercion semantics and subtyping is this idea of coherence. When you have coercions to handle slowdowns from subtyping, some of the coercions can actually have an ambiguous effect, which creates this substantial problem that the programmer can't predict or control what its programs might actually do. Therefore, you have to make use of what's known as the coherence principle, stated below. Intersection types are another important aspect of subtypes, the subtype sort of theory that we've been discussing. There is an intersection operator, which when used allows for the actual creation of a type that is the intersection of two other types. There are, to do this, you need 4 new intersection subtyping rules, as shown here. Aside from intersection types, there are also union types. This is a type that contains all values that belong to either t sub 1 or t sub 2. You also have a union operator, which is how the type is created. And notable about this is that there are no origin tags for either element. Subtyping has a long history in computer science. It began in the 60s. One of the problems they encountered was that typing with records, as mentioned before, was very complex. Two computer scientists, Cardarelli and Mitchell, invented a new calculus to deal with this in 1991. Other alternate calculuses, although less popular for dealing with typing with records, exist, such as the row variable polymorphism.